two-dimensional bodies, drag force. The drag of some representative wide span bodies is shown versus Reynolds number in this picture. All bodies, the various bodies shape smooth circular cylinder as shown, square cylinder, plate normal to stream, and also surface plate parallel to stream, such as this shape, and airfoil, venturi, pigeon, and other shapes in the stream shown in this picture. All bodies have high drag coefficient at very low creeping flow Reynolds number. At higher low Reynolds number is shown with and called creeping flow. While they spread apart at high Reynolds number according to the degree of stream lining, all values of drag coefficient in this picture are based on the platform area except the plate normal to the flow. This type. No, this. The birds and the airplanes are of course not very two-dimensional, having only modest span length. Note that birds are not nearly as efficient as modern sailplanes or airfoils. We have the definition for description creeping flow. In 1851, Stokes showed that if the Reynolds number is very small, the acceleration terms in the Navier-Stokes equation, acceleration terms vanishes. The flow is termed creeping flow. Or Stokes flow. And is a balance between the pressure gradient and viscous stress. As we know, we had this relation for example, for average Stokes model, we can vanish the acceleration term and also the G effect. Then we have a balance between delta P equals to the delta U, delta P. A balance between the pressure gradient and viscous stresses. If the geometry is simple, closed form solution can be found and the body drag can be computed. Stokes himself provided a sphere drag formula for as this relation. The drag formula for a sphere from the Stokes expression is and CD equals to which is equals to the on Reynolds D. The drag coefficient for a sphere, let me write a sphere, also we have sphere here. The relation is plotted also in some diagram, especially in previous diagram. We can have the drag force coefficient for a sphere and Reynolds at Stokes law takes normal to the stream and various sphere, A-shape ball and ellipsoid shapes are provided in this picture. There are also tables give a few data on drag based on the frontal area of two-dimensional bodies of various cross sections at the Reynolds. The sharp edge bodies, which let me provide the tables related to the drag coefficient for SQL cylinder. Drag coefficient is CD based on frontal area. Other shapes are also available in this table. The square cylinder is two types, from the side and from the angle. The various drag coefficients are obtained, and also for semicircles, line and semicircles area, triangles into front area, plate normal, thin plate normal to wall, and hexagon are also available. There is also another shapes information drag coefficients which are provided in this picture. Rounded nose section with values L and H. Here we have various drag coefficients. For flat nose section with L and H tables, and various drag coefficients. Elliptical cylinders also available in laminar and turbulent flow in this table. The proportional of two chords for various ratio of chords have. This table shows the various drag force coefficient. There are also some example solution videos in the channel video. Some drag coefficients of three-dimensional bodies are listed also in this table. Again, we can conclude that the sharp edge always causes flow separation, and high drag that is insensitive to Reynolds number. For the 3D shape, we have various data in this table, also available in the reference. For a cube, cup, disc, and parachute, low porosity, and train, for example, bicycle and tractor, trailer, truck, human bodies, porous, parabolics, short cylinder, and cones. With various theta, L and D, and porosity, we have various drag coefficients in this table. There are also some another shapes which listed here also. Rectangular plates with the geometry specification ratio. Here we have various drag force also. For an ellipsoid with various ratio of L on D, we have for turbulent and laminar and turbulent flow drag coefficient. The Reynolds accuracy is also determined. For a flat faced cylinder, we have the drag coefficients based on L on D. The next description in this chapter is: note that the sphere data are for fixed model in wind tunnel and from failing sphere test, and indicate a drag coefficient above mean in the range of. So for a sphere, buoyant rising light sphere. There we have data on the table and also figures for the sphere. For fixed model in wind tunnel, and from failing sphere test, and indicate a drag coefficient of about NIM 510, excuse me, in the range of Reynolds D. That is not the case for freely rising buoyant sphere, or what is if the sphere is light? So if the sphere which have a condition, for example, the density of the sphere smaller than the density of the fluid consumed as the sphere is light, a weak instability arises in the range of instability rises in range of the sphere then spiral upward at angle of about 60 degrees from the horizontal. The drag coefficient is approximately doubled to an average of for the light sphere. For the behavior of, for example, light sphere, we can use the drag coefficient as this relation.